Today I will be the moderator. My name is Niehaus. I'm at the University of Twente. I did my postdoc with George Whitehead at Harvard University. And after that, I was for almost 11 years in Singapore, where I was an assistant professor, then was promoted to associate. But about 2 years ago, I moved back to the University of Twente, where I'm from, to continue my studies. Yeah, and very closely related to topics that will be presented today by Professor Takhee Lee. And his topic will fit, in the topic that was already, basically the theme of the whole month, across nano divide. We already had fantastic speakers earlier this month, and Takhee Lee is today's speakers, and he will close this series for the July component. The whole panels, the discussion is moderated by me. Takhee Lee is the speaker. One of the panelists is Martin Thuo, and of course he's a very well-known guy in this platform. And the other panelists are Wang, Jun Lee, and we have also an ex-challenger, Ju Lee. Later, I will introduce them more properly with a little bit more detail. But let me now introduce today's speaker, Takhee Lee. Takhee Lee is currently a professor at the Department of Physics and Astronomy at Seoul National University, SNU, Korea. I know him already quite well because I visited him when he was still at Gwangju University. But he moved from there around 2011, I believe, to SNU. To basically continue his work on all sorts of aspects in electronics. He makes electronic devices based on single molecules, self-assembled monolayers, polymers, semiconductor, nanomaterials, really a lot. It's very impressive what he has done. And that is also really reflected in the large number of awards he has. It's a long list of awards. It's a little bit too much to mention over here, but he also is very active in the community, and he's an editorial board member of quite a few journals: Nanotechnology, Nanofutures, ACS Nano, and Advanced Electromaterials, for instance. So herewith, I would like now to give Takhee Lee the dance floor so he can present his seminar.
Okay. Should I? Okay. Okay. So can you see my slide and raise a point?
Yep.
Okay.
Yep.
All right. I'm gonna start. Thank you, Chris, Professor Niehaus. Yes, I'm honored to give a talk online. I think this is a famous talk throughout the world. And my name is Takhee Lee. I'm currently a faculty in Department of Physics, the Seoul National University. And Chris mentioned that I will give a talk about molecular scale electronic device, which is meaning the fabricate electronic device out of the molecule, or single molecule or molecular monolayers. All right. So in my group, I study electronic device made of a few materials, in molecules, or polymers. These days, I'm also studying to perovskite, 2D materials, graphene. Particularly, I'm using graphene as electrode. But today, I'm going to focus on the molecular electronics, which is an electronic device made with the molecules, single molecule and molecular monolayer. As you can see, these some schematics. Okay, this topic that I've been studying this topic in past like 20, more than 20 years. I'm still studying this. Okay, I'm moving this window. So this is a famous slide that is kind of a starting point of this research field, which is molecular electronics. It is a proposal of a theoretical proposal by Abraham Rechtner about in 1974. So the element was made with this molecule. The length is about 2 nanometer from left to the right. So it composed of 3 components. One is D, the donor, electron donor, and acceptor is accept the electrons, and it is a bridge between this element. So acceptor like to accept the electron first, and then pass through the sigma bridge, and then donor will donate 2 electron to the electrode. So there is a one directional is favorable than the other direction, which is a diode. So this is calculation result. For example, this is PN diode. This is a mimic of the diode. So, but in realization in the real device is really difficult. It took like 20 years from 1974, and around the 1997, the people were able to really demonstrate in experiment. So the cell percent monolayer, this is one of the famous way to fabricate molecular structure. Langmuir-Brazil is one of the famous way, and self-assembled monolayer is another way. Okay, it is known to develop in 1984. Many people, including Bellek group and George Whiteside group, and the method of this form of the cell-percent monolayer is you simply deposit the molecule you simply drop the substrate into the solution containing molecules. The molecule end group particularly can chemically bind to the substrate surface, and then between the molecule between there's a van der Waals interaction, it forms a order structure. Okay, this is a way of the cell-percent monolayer. And here's the example. I got the image from Paul Weiss, from editor of SS Nano. And the molecule here particular is called alkane thiol. The thiol is a sulfur term in usual chemistry community. And this thiol is known to chemically bonding well on gold substrate. So it forms like this way, cross-sectional view, and it tilts like 30 degrees on gold. And when people examine using the scanning tunneling microscope, and the tip, you can imagine there's a tip, sharp tip, metal tip on top of this surface, and it imaging on the top end group. So you can see this actually CH methylene group on at the end of the molecule. You can see this order structure. But this looks like very order structure, but if you scan wide area, like 25, still small area, but 25 nanometer, you can see some grain boundaries, and it's vacancy island. If you look at the 60 nanometer, and you have this bright, middle, and dark area is actually from gold stack. The substrate is not atomically flat. And in addition, there's an island grain boundary. You can see some line pattern, which is one direction, there's another direction, the grain boundary. So those are vacancy and grain boundary act as a defect when you fabricate some device structure. Okay, so we have some order structure, but it's not perfect. Okay, I have one slide to briefly introduce electronic structure when you form a molecular junction. So imagine there's one molecule. This name is benzene diode. The diode connect to gold in both ways, and this benzene ring. And this length is about 0.7 nanometers. So when one benzene molecule connect to electrode, and people were able to calculate the density of state. And for example, I used to simulation is available, simulation package available at Purdue University where I got the degree, PhD. And here's a LUMO, meaning where I have to explain this first. So this is number of atoms is so small, So you can imagine like hydrogen atoms. It's a little bit different from the bulk solid state. There's many atoms. When atoms periodically oriented, then you produce a conduction band and a valence band. But in molecular junction, it forms like orbital. So in the lower orbital occupied by electron, and upper orbitals are empty. So you have a top highest occupied molecular orbital corresponding to top valence band, maximum valence band, and lowest unoccupied orbital corresponding to bottom of the conduction band. So it's a little bit similar structure, occupied, unoccupied, occupied, unoccupied with a band gap. So we have a homonymous gap, this energy band gap, but different thing is that this is a band, this is an orbital, so we have some difference. Okay. So in benzene diode, with a gold context, it has LUMO, HOMO. There's a broadening corresponding to this orbital. Broadening is due to a temperature effect, and also continuous electron state coupled to isolate individual orbital state coupling will produce some broadening effect. Okay. So the band gap LUMO, HOMO, homonymous gap is about 4 electron volt. So in semiconductor, 4 electron, the diamond is insulating is about 6 electron volt in band gap. So 4 electron volt usually considered as insulating, but this is the length is so small. Although it's largely band gap, but length is so small, there will be a lot of current path component because of tunneling. So that's something I will explain a bit. So I'm sorry to have to show some many equations, but I don't want to go detail. But in it is kind of famous in when you have molecules one dimension. See, this is a one dimension channel. So when you imagine one gold atom in one dimension, it will get because of the density of state is one dimensional property and velocity of electron that will give to leading to so-called Landauer formula. And this factor here is the current transmission electron probability passing from left electrode to right electrode. And this F is a Fermi energy where the electron is occupation probability, but this factor is given to so-called quantized conductance due to the one-dimensional channel. Okay, so basically you can calculate if you calculate the T transmission probability very carefully. Okay, and we can calculate T, for example, as an electronic described as wave function, then we can calculate T like this, or people can calculate more quantum calculation method. The T can be calculated this way, is a coupling. And T also can be calculated by Siemens model, T. So in that case, when you the Siemens model T transmission probability calculated by a so-called WKB approximation, and it gives to result famous result of the current density is exponentially depends on the length of D, which means the length of D is D right here, the molecular length, okay, length D, and current or resistance exponentially depend on D with some coefficient of beta value. So this beta value right here, is right, not here. Here, right here, this beta value, right, you can see that T is exponentially depends on D with a 2 kappa. So beta is like a 2 kappa. Okay, so this beta is called decay coefficient. Basically, how quickly electron decrease within the barrier. Okay, insulating decrease quickly, more conducting media decrease slowly. So the insulating, the space, the vacuum insulating is the most insulating media, which is beta value is about 2 with some unit. So I will talk about also the beta value of this molecular media, what is typical values. And let me, and also not only the barrier height is also the factor of the current transport. If it's high barrier, it will be more difficult to pass. Less barrier is a little bit easier. And then when you apply the bias more than a barrier height, this is a bias. If you apply bias more than barrier height, your barrier shape changes from rectangular type to triangular type, which is actually onset of field emission. Okay, we call Pauli low time or field emission, which is the same. It's something like when old cathode ray TV, they apply like 600 volt, will it will create a field emission of the electron shooting from filament. So this is the actual onset. So by comparing tunneling rhythm with a low bias and high bias with a field emission rhythm, you can distinguish this relationship, and you can get some idea of what the barrier height is. So this is a so-called transition voltage spectroscopy. And when you plot certain quantity as inverse of bias, then low bias is tunneling, which is direct tunneling, and high bias is field emission tunneling, and you change the two rhythm. So those rhythm is happen when bias is roughly equal to the barrier height. So it gives the idea of what the barrier height, which meaning the barrier height meaning the energy level of the orbital of the molecule. So sorry for about a few slides of mathematics. So let me go back to some experimental result. So in our group, we fabricate this junction, a single molecule junction, or monolayer junction. You can see this is a single molecule between the electrode, or many molecules between two electrodes. So we fabricate that, and then we study what the detailed mechanism, for example, and the contact effect, and then molecular dependent effect. And there's many electron molecular interaction effect. So those are a subject that we are studying. And you can imagine it looks like easy to draw this PowerPoint, but in reality, it's really difficult. Okay, because of the length is about 1 nanometer or 2 nanometers, so it's difficult to fabricate electrode across this molecule. People try to fabricate junction, and it happened to 1997 in my postdoc, when I was postdoc Yale, and they create a very thin old wire mechanically break, and then trap the molecule to broken side right there. And another group at the Cornell and Harvard, they did to make a pattern and then flow high current, and then they create a nano gap by Joule heating. So they call electron migration nano gap. And the advantage of this structure is a transistor structure, which is source electrode, drain electrode, and bottom of this the screen, the gate electrode. So there are 3 terminal, which is a mimic to transistor action. Conducting FNS. Those are examples are studying one molecule or small number molecule. In comparison, nanopore junction, which is the diameter is about 50 nanometer or microscale, and this EGAN group, Herbert and Chris and Martin were from Harvard group, and they're pioneer using the EGAN from initially mercury electrode, and then they moved to EGAN, which is much better choice studying to the molecular junctions. So they did a lot of the study in EGAN group, and the PWP is conducting polymer can act as electrode. Those are examples to study many molecules, like the bundle molecule, which is the average effect. So this is a Mark Reed group at the Yale University, and at the end of my talk, I will tell a little bit about Mark Reed. So this is considered as the first experimental result to study measure the conductance through the single molecule. So they trapped the single molecule, benzene diode, by using the mechanically broken method. And then this blue is experimental result. And then this green, I myself calculate. Okay, so you can see this pattern is this is a band gap. Okay, like exactly it's 4 times some energy barrier height. So this gives you an idea of the band gap of the molecule. And then this is mechanical junction technique. So it cited a lot. And Cornell and Harvard group, the electron migration. So let's see if I click. I delete this. Maybe you can see this is how they fabricate. I got this image from their group. Oh, sorry. Here. Okay. I hope you can see this movie clip. So there's a very thin area, and you can see the cracks. So they stop at the 4 Kelvin and they trap the molecule and they measure this. So what they are measuring, for example, when they are cobalt containing molecule. Okay, let me change my mouse. Cobalt containing molecule and to the difference is a long end group and short end group. Depends on the coupling. They create some Kondo effect, which is the interaction of the spin, or Coulomb bracket, which is act as a quantum dot in the middle. So they observe this like pioneering pyramid. And 2003, well, those are some physics science understanding, but people start to demonstrate like a device and memory. So this is early example that Hewlett-Packard and UCLA at that time, and its molecule here is a low-tech molecule. The length is about 2 nanometer, although you have a lot of element, but 2 nanometer. And you can see the link, this link is moving left and right, depends on position. The conductivity of the molecule is different. High conductivity and low conductivity can act as on state and off state as memory. And this is a molecule synthesized by Fraser Stuart, and he got the Nobel Prize at 2016 as a topic of molecular machine, mechanical molecules. So they create 8x8 crossbar structure. There is a 8 electrode at the bottom, the molecule in between, and top is 90-degree cross and top 8. So 8x8 total 64 bit. And then they observe this high current and low current. So they load and 0, 1 is ASCII coding indicating HB impact. The stability yield is poor, but later on this group they have improved the yield and the stability and even increase the density of the cells. But this was actually the idea of this architecture, crossbar architecture, was the pattern, and actually this is basic architecture for so-called MNAM and recent memory device. Nowadays, people are using this based on this structure. They're studying neuromorphic computing. Okay, let's go back to my work. So I gave it to about 20 minutes of the background. So this is where I did some study at the postdoc at the Yale during the 2004. And I already told that it's very difficult to fabricate the junction. The reason is this is so thin. So the molecule can self-assemble on the bottom gold by solution method. So it automatically forms with a little bit defect, but it's kind of older structure. But top electrode, you have to provide the top electrode. Say, let's say you evaporate top metal on top of the molecule. This is 2 nanometer. The top metal can easily penetrate this 2 nanometer thin object, and touching down the bottom, it creates electric short. So these are all the defect. Okay. So when I was there postdoc, I evaporate the top metal in the chamber evaporation chamber, and while flowing liquid nitrogen, so which meaning that it's slowing down the energy of the atomic gold atom during evaporation. Okay, even though in this long time process, when, for example, I fabricate 1,000 junctions, molecular device, and only about 10 devices working. So all 909 device is dead because of the electric short problem. The short meaning just is a electric short wire shorting problem. But 10 junction is not enough statistically. So when we plot this current density as a function of length, so this is number is short length, long middle length, and long length because of the number of chain here. So you can count this chain 1, 2, 3, 4. This is the number of chain, and then so long length is a D. I told you exponential dependence of D. So more longer current is lower. So if this current is lower, that's correct. But here between 10, 12, this is the opposite trend, which means due to the statistically not enough. Okay. So there was difficulty. So this is one reason why the people at that time studying the molecule kind of gave up and moved to different topic because it's so difficulty in the fabrication. So after I finished my postdoc, I came back to my first position in Korea faculty in Gwangju City, and I studied with my that time student. We fabricate many devices, and the junction area 2 micron and sometimes 50 nanometer is similar structure vertically, but we fabricate many junctions. You can see 1 centimeter contain about 300 units. So if you take a 10 1 centimeter, you can have 3,000. Okay, so the problem is how you can measure many junctions. That's more difficult. Fabrication is okay, but measurement is more time consuming. So students measure, like for example, they fabricate 30,000 junctions, and they measure individually. We didn't have automate probe stations, so if my student measure individually, you can imagine how many junctions you can measure per day. 100. If you measure 100 junctions, it takes 100 days. Okay? So you have to measure like 1,000 junctions a day, then you can finish like how many? 10 days. So yield is 1%. I told you there already about 10 working out of 1,000. So if you just 10 times we multiply, then 100 is working out of 10,000. So that number is similar. So 30,000, okay, about 13,000, about 100 is working. Here is 14,000, about 100, 200 is working. There is a notation CA, meaning monothiol. There's a good binding thiol, but poor binding on top. Dithiol, D means dithiol, both are good binding. So you can study the difference of contact reasons. How is this is good contact, bad contact? What is the difference between the contact property in the junction? So we study that. For example, poor A is a similar current that good tag. So good longer tag is similar conductivity was a poor A. And between same length, poor A, good A is a conductivity difference about 1 order magnitude. So before this 2007, we didn't know the conductivity difference between the junctions, but now we have some statistics out of 30,000. Then we study that the difference of a good contact, poor contact is about 1 order of difference, which is actually not a lot. It's a small difference. And other students fabricate smaller junctions. This so far is 1 micron, 2 micron, but if you fabricate 50 nanometer, so one of my students fabricate about 7,000, but even lithography of a junction of 50 nanometer, the yield is increased from 1% to 6%. It's basically the shorting problem is whenever the metal filament touching down from top to bottom. So when junction is small, this probability of shorting problem is decreased. So that's the reason. But still, 6% is not enough, okay, from industrial point of view. So many people will study to how to improve this yield from like up to the 90%. This I will explain later. This experiential dependence and experiential dependence beta value, how quickly electron decay, and it depends on material. So this is an insulating material, it's conducting material, the conducting molecule, insulating molecule. The insulating molecule is about 0.8 up to 1.2 with the diffusion unit. I told you the 2 is the vacuum, which is the best insulating media, and conducting molecule is about 0.3 to 0.5, which is less value because of the more conducting. Okay, so we can get this tunneling experience, tunneling physics mechanism, and by using nano gap feature, I already explained that you can create a nano gap here by electrolytic Joule heating. And the nice thing of this structure is you have a bottom gate electrode. So it's a source, drain, gate, which is a 3 component of the Philip transistor. So by using fabricating this structure, this single molecule junction, and it measures 4 Kelvin, then you can get the transistor action by orbital. You can see this. So this is a HOMO is occupied valence band, which is this is a p-type. When you apply minus gating, this energy is moving up by applying minus gate voltage. So this is how we do that. So when you apply minus voltage, the current goes up from this color to black color current increase, which is an orbital transistor. And we repeat this band is a band transistor, which is silicon. So this is molecule is act as p-type orbital transistors, but is 4 Kelvin is not room temperature. So it is in principle, it acts as a Philip transistor out of the orbital controlling. The yield of how to fabricate this single molecule transistor is even worse than this structure. So here is a typical yield is about fabricate more than 5,000 up to like 10,000, and it ends up like about 30 devices working. So the yield is even more difficult, single molecule junction. And this is all the working device. So you can count this about 35 junction. And there is insulating molecule, single molecule transistor, and this conducting molecule, single molecule transistor. And the conductivity, this conducting is higher than this conductivity, than like about 100 factors. So you can see the conductivity 0.01 times something, the 10 to the minus 5 times something. This G0 is one-dimensional quantum of conductance value, is known as this value. Okay. So the yield is poor because of this is because of the electron migration. When the gap is wide, too wide, it's already open. If it's too short, it's a short. So that's the reason you need to perfect the length of the matching to the molecule. That's the reason why yield is so poor. So in comparison, the mechanical opening is better in the yield. So here is, for example, by moving this piezo, moving up and down, you can open, widening, and shorting the gap. So you have has a higher yield. You have a chance of a higher yield. Okay. So here we at that time, Professor Dongxiang is currently in Langkai University, and he was at that time my group with a research professor, and we did that mechanical junction with a side gate right here, side gate. So this is side gate can tuning the orbital, and this is what we observed. So when you breaking this, initially gold breaking right there, and then breaking more, this is molecular breaking. This is a single molecule benzene, so about 0.01 times G0 value. So we at point here, we do the orbital. So the yield is about 10% compared to yield was nano gap was 0.1%. Okay, so the yield is at least we have to way to produce more reliable junction with a high yield. So let me explain some the method to produce high yield. These days, nowadays, who have the researcher studying molecular junction, they are doing high yield. Okay? So the first idea was demonstrated by the European group, and they did to simply deposit conducting polymer, which is PWS polymer. So that polymer is softly touching down with the solution process on top of the molecule. It is not scale. This molecule thickness is about 2 nanometer. The PWS is about 100 nanometer. But this PWS provides interlayer electrode on top of the molecule. So although the detailed interface between conducting polymer and molecule is not clearly known, but in terms of the device performance or reliability was excellent. Okay? And then we learned from these ideas that we used at the time. The graphene is famous material as conducting electrode. So we deposit conducting electrode similar. You can simply replace PWS by graphene films. Okay, so you can create a film and yield is about 90%. And also something you can spin coating on the top metal. So reduced graphene oxide as conducting element, you spin coating that, and then also you can have high yield. So this is an example of the high yield structure using this approach, PWS conducting polymer. Because now, if this is really a high yield platform, then you can do the flexible. The organic electronics is advantage of organic electronics is flexibility, okay, in comparison to silicon devices. So we fabricate flexible molecular junction on plastic substrate. So here is a substrate plastic and bottom gold and molecular monolayer. Here is an interlayer of PWS right there. So molecule is insulating molecule with different lengths. C8, C12, C16 that I told you many times. The insulating with different lengths, and then and we can measure the. Okay, sorry, this I will change back to. I'm sorry, a little bit noise, but this is how we measure that. We can do the flexible measurement. Let me stop this. So we do this repeating this cycling of the bending cycle. Then we measure that this is images, real device, and the junction yield is great. So great. So this is we very stable. High current is short length, middle current, middle length, and low current, long length. And then you can lining up the toothpick, which is a 1 millimeter radius, and we can even twist up to the 30 degree, and this all possible. So yield is about when you measure a flat configuration 100%. You can see flat configuration. If you're bending a little more, some device died, but still more than 85%. If you're bending even more, still yield is 85%. And when we didn't do any bending cycling, initially 100%, 100 cycle bending. I showed the movie clip that we repeating this, and then we take out the sample, measure again about 85%, and 1,000 bending still we have 80%. So this is a little bit distribution current. That distribution current is due to the flatness of the bottom surface. Okay? The bottom gold is not atomically flat; it's a little bit roughness. So because of that, we have a little bit roughness of this current distribution. But you can clearly some different area of the long molecule, middle molecule, short molecule. Okay? Yield is 80%. So by taking now we have a high approach. So by using high approach, we don't have to fabricate any more 10,000 junctions. Even 100 junctions is enough. Even 50 junctions is enough. If it is yield is 80%. So let me give some example. We study using high yield platform, either graphene or PDAPSS conductive polymer or reduced graphene oxide spin coating, or many other ways. Photo switching and other examples. Okay. So one example that you can transfer not only graphene but also metals. So let's say we have a gold film on some layer PMMA, then we transfer gold. So this can be conventional gold molecule, gold junction, but transfer yield is about 60% to 80%. Okay, or average about 70%. So this insulating molecule, short, middle, long. You can see this. We do that graphene, right? Similar with graphene transfer from the stamp to graphene on top of the molecule layer. So it's still the same, similar. The insulating molecule, short, middle, long. We have about the yield is about 60 to 70%. Okay. And not only the insulating molecule, we can do the conducting molecule. So beta value here is 0.3, right? You can see. But this beta value, I don't have beta value, maybe about right here. Beta value is 1. Okay. So this beta value 0.3. This is also bending structure is possible. The graphene electrode can be chemically doped by applying this so-called this molecule on graphene. It withdraw electrons, so it doping as a p doping of the graphene, which p doping you increase work function of the graphene. So the graphene, if you increase work function, actually this metal is going down to better matching with the homo level, which is currently increase if you doping is p-type graphene electrode. So that's what we see before the graphene doping, and after graphene doping current is higher. So let me give example of the conducting the photo switching molecule. This molecule, the length is about 2 nanometer. Molecule was provided by the German group, and you see in the middle there's a bonding connectivity. By shining the UV, it connected, which meaning overall connectivity is good, better is high conductivity. If shine the visible light, it disconnect, open. Then overall connectivity is poor, so the conductivity is lower. So this on state, off state, and we shine the light. By first approach is PDAPSS. This is high yield. From now on, we don't do any low yield process. Everything is high yield process, either PDAPSS or graphene or metal transfer, anything. So this is a PDAPSS conducting polymer, and we shine the light, and this is our result. This is on state. After we shine the UV, this is visible, is off state. So we have this high current, low current with a difference about 1 order magnitude. But the problem was we failed to show reversible switching, which meaning we couldn't switch really, but it was remain as on state or off state whenever we fabricate the device on only environment or UV or off environment or visible. So it remained as there. So we couldn't switch it. The reason is maybe at that early time, our power was not enough, or the overall transmission of the light was not enough. The energy was not enough to give it to this reaction. Okay. So the next approach was we change it to reduced graphene oxide spin coating on top of that here molecule instead of the conductive polymer. So this is still the same. It's on, off by shining UV, by shining visible on and off configuration, flexible, high yield. But now we can switch this. Okay, you can see the switching, this switchable. And this overall picture is a switchable off, UV shining on, visible shining off, UV shining on, and repeating, and so on and so on. Okay, although the time of the individual switching time, this is not short. So this is not short. This switch is, if I remember, is about more than like 20 minutes. It's not like 1 minute or 1 second. It's like tens of minutes, which is still really well. There's a way to improvement, but at least we have a possibility of the single molecule junction with a high yield as some kind of function. Okay. So third approach is what will happen. What you apply multi-layer graphene in, but this maybe is better than reduced graphene oxide of the second approach, first approach. So we did that the same molecule, and then so this is also on and off. Okay, but in that case we only observe transition from off to on, but we couldn't do that transition from on to off. So this is called unidirectional, or you can call that warm device, which is write once, read many times. You can make on off one time, but you cannot change it at all. So you can, like CD, when you make a CD-ROM, you can make one, but you cannot change, right? So, but this is also useful, the warm device. And the mechanism of this why is warm device is this is warm, off to on, we can, but cannot on to off. And the mechanism is that we understood that by calculating this all kind of dense of state of the coupling, then when this is an on state, off state, which off meaning coupling is weak. So the molecule has identity, and then we can do some reaction of the molecule change. But when you on state, coupling is so high, and the molecule is losing their molecular identity because of the hybridization property of this overall junction with the graphene. So we quenching out of this molecular identity, and we lose to the switching property principle. So we can change it from off to on, but we cannot change it on to off. That's the we interpretation, but yeah, by collaboration with the European group, that's our conclusion. So that is actually I finished the from background to some research achievement in our group history, and not only the molecule itself, we study how the molecule can help to other related topics. Okay, so as Chris mentioned that I'm studying a lot of nanomaterial as electronic or photonic devices, and how we can use molecular heterojunction, and how we can use molecular in other research field. So for example, and molecule gold molecule graphene, that is a one metal junction, but perovskite is good material that is known to observe the light to create the extron, electron hole photo generation, and is very good material for, because of that, very good material for solar cell and LED. So we shine the light with this heterostructure, perovskite, graphene, molecule, and bottom gold. So if you imagine the shine the light, perovskite react first, and it creates a lot of charge, and the charge, due to the energy alignment, the whole transfer to graphene. So graphene can change energy property, and that has helped to of the overall molecular junction property. And also molecule, we can do a little more the variation that by using the dipole direction, different dipole direction molecule, which is up direction, almost no dipole, down direction, that this electric field will enhance of the whole transmission or block the whole transmission. So for example, here, this dipole plus, the whole is coming from perovskite to the graphene. So plus is up, this I think that molecule is a little bit hinder, blocking the whole coming from perovskite to the graphene. But that opposite dipole, actually the minus part over here is the enhance of the whole coming from perovskite to the graphene. So that is actually more increase by shining, is less increase of this shining. So we can do some, this is one idea of the how we can utilize heteroelectrode structure. Okay. And this is another example that heterostructure meaning gold molecule, gold, but here is a heterostructure. The MS2 is a 2D semiconductor material. So we have molecule is kind of a dielectric material and semiconductor, and then metal. So you have a metal semiconductor junction. That junction will have some energy alignment of because of the metal semiconductor pinning. So by overall this, and you can get some easily tuning that creating to a diode. So this molecule is not that diode molecule, it's not symmetric molecule, but because of this, the introducing this MS2 semiconductor, you can get the diode behavior. And this actually, the mechanism of this is this MS2 semiconductor energy band is you can allow here over the path and disallow over the path. So you have a long distance of a current path and short distance of current path, which is a similar mechanism that the Chris famous work in late of 2000 that he studied the ferrocene molecule of this mechanism of this. So we are using symmetric molecule and using this introduction by simply the semiconductor 2D material that you can get this 2D diode behavior. And what else? The molecule can also be used to in other material, like the 2D material is one of the famous material that many people, physics and engineering, study this. And this 2D material, particularly the MS2, is known have a lot of sulfur vacancy. So schematically here sulfur vacancy, and this is a kind of mechanism of why this MS2 is N-type. So if you're using this sulfur diol molecule treatment, then this diol sulfur end group will likely to bind it to this sulfur vacancy, which meaning sulfur vacancy is donor N-type, but if you passivate, you reduce the donor concentration. So by applying this, the conductivity decrease and dopant charge density decrease because of you losing more density. Okay, so here is a current decrease, and so we observe that current decrease. But mechanism is real. Is this really? What is here? Is it really? The question is it really due to of the donor reduction, or is simply something alien molecule on surface we give to surface scattering, right? So we studied that difference between these two mechanisms, and we kind of interpret what the dominant mechanism, which actually indeed the sulfur vacancy. And I will skip this part. And the molecule, what is 2D material is when we try to doping the 2D material, but people dope the silicon by substitutional atoms. Like if you deposit arsenic or column 3, column 5, the silicon change even the gallium arsenide by choosing the proper element that it can be doped N-type or P-type. But 2D material like this here, for example, WSC2 or MS2 is very difficult doping with a substitutional way. Okay, so one idea is this is very thin. So if you deposit on very thin material with some molecule which has charge transfer properties, and this material is known to withdraw electron. It's donor. It's a doping the whole doping, P-type dopant. So this is due to the energy alignment. It is the electron from the WS2 coming from WS2 to the molecule. So this can be withdraw electron. So this is P-type dopant. So this can be P-doped with this surface. So simply to deposit on molecule on top of the matter, because this is working. So-called surface charge doping is SCTD is working because of 2D nature with a very thin nature. And this is working. And then, but let's say you have this, and then we study these 3 molecule, and this current increased by more doping, but this is a surface on top of the surface material, so it causes surface scattering. So you have some surface scattering, impurity scattering. This mobility as function of temperature with down to 10 Kelvin, so phonon property and impurity property. So you have I think this is undoped this is a pristine undoped. This is surface doping. So mobility decreased because of the surface scattering. So let's say how we prevent this surface scattering but with a doping method. You simply blocking a thin layer between these. Okay, kind of modulation doping by blocking this. So let's say we can put the very thin layer of HBM, the bottom right. So we can see this is dopant. Right now, BB molecule is actually anti-dopant. This MH2, and then here's a very thin of HBM. So that blocking the surface scattering, but it can also help to charge transfer as dopant. So let's say here is about the thin. It should be very thin. If you're too thick, it cannot be doped. Here is about 30 nanometer HBM, too thick, so cannot be doped. But 2 nanometer thin, it can be doped. So it's before and doping. And I think I don't have a mobility function plot, but it also decreases the surface scattering. So this is a modulation doping method, remote charge doping, and it has as an efficient way to doping and with minimizing of the surface scattering effect. Okay, and I have about 5 minutes. What about other material, the polymer? So this is a polymer FET. The polymer is PBTT, which is a P-type, one of the known as P-type channel. So this is a typical FET, source, drain, and gate. And then we have this the PBTT is channel. Okay, and the doping of this polymer, usually people are doping with a mixing A and B. So A is a PBTT, and then you mix it with some charge transfer element. We are mixing together. But that doping is you doping everywhere. Okay, but if you're doping everywhere, then this doping is too doped, highly doped, and then it is not anymore semiconductor. So in semiconductor silicon, they are doping only the area of the contact, which is enhanced of charge injection by keeping the P-type or N-type, whatever the channel is. So only the metal implantation on the area of the contact by improving the charge injection. Okay, simply making the ohmic contact here more better ohmic contact. So we did that, and one of our his postdoc, he got the degree from Cambridge, and he was a postdoc at my group. Now he's a faculty in Seoul National University. And what he did in Cambridge, he did a evaporation molecular doping on molecular or organic polymer. So he evaporate so-called FFTCNQ, evaporate, and those is not mixing solution. So evaporate it stay in local area. So what they published in paper, and he got the idea why using this idea to deposit only the contact area. So FFTCNQ contact area. So this can be enhanced the charge injection. So and then here injection charge injection currently improved and mobility better and many good sign. And one weakness of this problem is although we deposit contact area, and this is still molecule, so it has a little bit diffusion into the channel. It diffusing into it. So that's the reason why we surface etching a little bit. So the second idea was, although we deposit contact area, it has a little bit problem of the diffusion still. So why we blocking diffusion? So we blocking diffusion in the middle. So this is a difference of FTCNQ dopant. TCNQ is blocking, is not dopant because of energy alignment. This is simply blocking. So by applying contact doping plus blocking so we can have even higher stability of this as time. So here is a cover picture. This is I will skip in detail, but this is one idea. Okay. All right. For surface control, I think I will skip that. Okay. So this is the end of my talk, and I'm studying molecule and polymer perovskite and 2D material. I give you spend more time on this topic, and also I give it to some idea how we can utilize molecules for different topics. And this is my collaborator, molecule and polymer perovskite and 2D atomic And also I collaborate heavily with a Chinese group, Group Dongxiang in Nankai and Group Xupango in Peking, and a European group, and Chris Niehaus from Netherlands, and with some of groups, we together published review papers, and also another review paper is coming from the different topic is plasmonic. I think the expert in the Chris, this plasmonic junction when you light interaction, the molecular junction. So this is probably coming soon. So here's my group website, funding in my group, and when we had coronavirus, we have to wear the mask. And so this is the end of my story, and I like to have a few minutes to talk about my supervisor, but postdoc at Yale University. Professor Mark Reed was my postdoc supervisor, and he's actually the pioneer in molecular junction and mechanical break junction 1997. Public Science, there's a citation like 5,000. This is the first measurement of the conductivity measurement of single molecular junction. That is actually experiment is boom up all the molecular program, and Chris and Martin Tour and many other people, and he's actually a pioneer. And unfortunately, he passed away in last year May because I guess it's heart attack. And we wrote actually an obituary in Nature Technology. And while we are with the other colleagues, when I wrote this, and then I didn't know that, but he's even more famous of a quantum dot. And he actually right here, he coined the name of a quantum dot in this published. This is also highly cited. So I didn't know the quantum dot was made by him, but he actually made this quantum dot by making three-dimensional confinement of semiconductor heterojunction. He named it as quantum dot. At that time, quantum well was a famous structure. So he combined more, and then he named it as a quantum dot. So he's actually APS fellow because of this invention of the quantum dot structure. Okay. So he passed away last year, May, age of 66. And he's applied physics and electrical engineering. He did the edit of chip nanotechnology for like 10 years. And he did a quantum dot semiconductor in Texas while he was Texas Instrument. And he studied to electronic transport mesoscopy. This is quantum dot semiconductor. And then he changed the topic to molecular junction. Okay, so he's a pioneer. And then he also studied to nanowire semiconductor as biosensor. For example, one blood drop can sense of the disease. That's what he did. So he said he coined the term of quantum dot and first measurement of single molecule junction and nanowire biosensor. And this is a few highly cited papers I got from Google citation. This conductance measurement of this 1997 is citation like 5,000, and that is single molecule with a large order ratio negative dependent resistance. The mechanism is not clear at that time, but this measurement experimental result was observed. Okay. And this is a nanowire biosensor, and this is a quantum dot semiconductor, and also this nanobio. And then this is the PIV paper we published the mechanism of tunneling, and there's also, and this is I told you single molecule orbital transistor together. So unfortunately, he passed away with heart attack, and then we are as alumni of his group that we wrote this obituary, and also we prepared a memorial issue in the nanotechnology journal where he served as an editor. That's probably coming next year. Okay, so thank you for your sharing this sadness. And with that, I finish my talk, and I will go back to my let's say my concluding slide. So thank you for your kind attention. Thank you very much.
Thank you. Yeah, thank you very much, Takhee Lee. Very inspiring talk. You covered an enormous big landscape and a lot of ground. Very interesting to hear the perspective. And yes, of course, I share my feelings with you. Mark Reed unfortunately passed away way too early, way before his time. But I really appreciate that you spent some some time to mention that. Before we go to the rest of the session, before the panelists will start to ask questions and an ex-challenger, we have two questions from the audience for Takhee Lee. The first question is from Wang, and of course he also compliments with the talk. And the question is about the reliability of photo-switchable devices. How reliable are they, and what about their lifetime?
Okay, the reliability, to be honest, is not highly reliable, and lifetime is not long. The yield is about, I told you yield at beginning of the fabrication, which is about 50%, 30%, 50%. But by measuring this, the yield, the reliability is getting worse and worse by repeating the measurement. So, I mean, when the molecule itself has a degrade when exposed to ambient. So we have to measure in good environment, but at that time I think we measure kind of ambient environment, so it degrades. So all the kind of packaging, we are not studying a lot of packaging passivation issue of the molecular junctions. But this is a lot of way to improve in terms of reliability and aging effect. But that's including to passivation and many other things. But if you passivate, we lose the power of light into the molecular junction. So there's also, you need the device architecture should be improved to prevent this power penetration. So we didn't spend a lot of time of this reliability and light aging effect, but there's something we have to study more.
But out of curiosity from myself, do you think the stability and the reliability can be improved through, let's say, molecular engineering? Can you envision that it is possible to make molecules more stable, or could you maybe simply package the devices better? Because after all, organic electronic devices are around us; they are commercially available. But I am very well aware that they've been.
Yeah, I think we need to study two ways. One is molecule should be stable element itself in the chemical point of view, plus the device structure, passivation, device top, matter, bottom, all that junction should be also stable, good. So we need to both of them. But I, as a physicist, I cannot really study the chemical point of view, but I study more focus on the overall architecture. But definitely we need to both of them. For example, that the photo switching molecule that you cannot buy from Aldridge's company. There's something once I purchased from some company, but it didn't work at all. Which meaning the company provide the molecule with something photo switching, but it's not. But the chemical carefully designed from German group there. Actually, I went there to Germany to get this molecule. So I got the molecule. I brought it in airplane. They carefully fabricate. So these chemistry people, engineering and physicists, they should work together. And that is interdisciplinary study is very important collaboration.
Okay, fantastic. And then the second question is from Jim from New Zealand. And also thank you for a very inspiring talk. For a molecular doping in such a thin layer, how to repair the defect if it introduced during doping?
Yeah, so the defect is there's a substrate defect called bottom, and there's molecular defect, molecular structure defect, and it's we cannot identify which defect mechanism of whenever you have some defect phenomena observed in measurement. But let's say the metal filament can be formed within the molecular junction. That is you can remove by opposite polarity, or sometimes it's working, sometimes it doesn't work. So I think it's a repair mechanism. It's not absolutely controllable, but it is not impossible. By training the device, sometimes so let's say device is the current increase, and then by applying measuring more measurement, the device can be settled down and stabilized. It's all possible, but it's not really more like it depends on a lot, because you cannot really, tuning these all kind of different factors. So it's in principle, it's difficult to absolutely repair the defect mechanism, but it's not impossible to, whenever this device is going dead, and then you should not give up the device. Okay, so there's also, I think this is also important issue that we have to really understand how we can understand the defect mechanism and how we can recover the mechanism. That's also important. I didn't spend a lot of time to think about that, but it's also a possibility, and there's an important issue.
Okay, thank you very much. Then let's move on, and let me introduce you to Martin Thuel. I think for those of you who are watching this fantastic platform every Friday night, they will know Martin very well. He's a very active member. I know Martin very well from our postdoc time. We were both at the same time postdocs in the group of George Whitesides. But then, of course, Martin moved on, and he's an independent professor at Iowa State University still. And he's working there in all sorts of aspects related to soft matter. And one of the things I like most is the really original things he does with liquid metal droplets, where he really finds very simple solutions for very tough problems. Our next panelist is Xiang Huang. He is at Tianjin University, but he's also the director of the Center of Flexible Variable Technology of IFED Tsinghua. He received his PhD degree in mechanical engineering from Columbia University in 2011, was a postdoctoral researcher at Urbana-Champaign from 2011 to 2014, and then he worked as an assistant professor in Missouri University before he moved back to China in 2016. And his main expertise is in flexible biomedical electronics. Our next panelist is John Liu at the State University of New York at Buffalo. He's there currently an assistant professor, but also adjunct faculty at Research and Education, Energy, Environment, and Water Institute. He received his PhD degree in 2018 in materials engineering from the University of Alberta, Canada. And there he was mainly working on power generation in dynamical semiconductor heterojunctions. He's published more than 30 papers in very reputable journals, including Nature Nanotechnology. And he won also quite a few important awards, including the Sony Faculty Innovation Award. And then our ex-challenger is Yu Li. She is at the moment a PhD candidate at Seoul Institute of Nanotech. And she has already published also quite a few papers in various journals, including Chemistry Letters, Flexible Electronics. And then I think it is really now time to move on to the second part of the evening, where now all the panel members can start to ask questions. And I think I would like to ask Martin to kickstart.
Thank you, Chris. For the sake of the nerves and giving the chance to the young member, can I yield my time to the ex-challenger to go first?
Okay.
Yuli, you can ask questions first.
Okay. Thank you, Chris. Thank you, Takhee Lee, for your great talk. It's remarkable that the single molecule can be assembled as the electronic devices. I'm curious that how to ensure that there is only one molecule between the electrons, and what's the requirement of the shape of the electrons?
Okay, a good question. It's better if I think, can I use my slide again? It's better to, if I use my slide, that's much better. The question was how we are sure if there is a really single molecule or not.
Yes.
Okay, so let me Okay, can you see? Let me change my go back to again. This okay. I'm searching that I have an answer for that the question. Let's see here, right there. Okay. So how we are sure we have a single molecule in this junction? That if this is a here you can see this is drawing. How we are sure that this number of conductivity, the 10 to the minus 5, 10 to the minus 2, is a kind of known that the single molecule conductivity. Although we have a variation, but let's say if this is like 10 times more, then that can be is not really a single molecule. Okay, so using this is an indirect kind of proof that we may have a single molecule, and also in the schematic, like this schematic, like you see, maybe she's a better picture of okay. So in the schematic, this so I will show you the mark read group here. Let's say this is a you can imagine single molecule junction, but it's gold, but the probability of the overall good connection maybe is 1 or 2. So other molecule, a little bit like a 1 angstrom difference in the vacuum gap will create about 10 order magnitude lower current. So it cannot be like 10 or more than 10 molecules connecting equally. It's more like 1, maybe 2. So those are in the distribution. We are not sure exactly 1 or 2, like here. It can be 2, this can be 1, right? So it is not really 10, but it can be 1 or 2. So, but we are not sure, we cannot put imaging technique, but it cannot be 10. So this is how we are indirectly claim that this is single molecule junction. And how we fabricate that, this is depends on the probability. We're breaking this by Joule heating this. So that is not really controllable. The breaking image I showed it like here. This process is probability, and that's the reason why we fabricate many junctions on many junctions of like this, which is about 5,000 junctions, more than 5,000, and end up like many junctions here is no current, open, too wide, too short, and then there's something between, and we collect that, and then we training the device, and then end up like about 30. So this is how we fabricate. So it's not an easy technique. So but I can say it is not easy.
Thank you.
Okay.
Thank you for the answer.
Okay.
And my second question is about the advantages of the molecular devices. We know the traditional semiconductor devices become maturity with many functions, such as the switch, memory, or the sensor. So when the size of the device decreases to the nanoscale, are these functions still realized, or can the molecular devices achieve some functions that traditional devices cannot? That's my question.
So your question is that is actually motivation of the why people study in the past, like molecular electron junctions. So one big idea was what happened if you miniaturize of the element. So silicon, if you miniaturize the element to the molecular scale, it will be different. Okay, so one of my mathematics slide like this. This slide is when silicon is like a big silicon is simmering down to one dimensional, and it behaves different ways. Okay, one dimensional quantized effect, and the molecule is the best idea, good choice of the minimum ultimate small building block. That how we can understand everything from big scale to molecular atomic scale, what will happen. That's the basic of the understanding of the science. But that is providing the understanding, but molecular itself is still, we have a problem of the industrial point of view, how we can make a reliable, high yield. Even how we improve the yield took like how many years? I mean, it took like improve the junction yield. This junction yield, it took like about 10 years, right? So, and then how we can really product out of the molecular scale junction, that will take another. For example, the memory device that I showed that the Hewlett-Packard memory device, those are, I didn't have the slide here, but 2007, they have a like a gigabit density demonstration of the memory, but yield is about still about 10%. But those are way to future direction utilizing. But these days, people studying to molecular scale junction can be, I mean, you can look at this, that can be a basic element of the numeric brain computing. But if you change this conductivity if you vary this conductivity with a multi-state level, then this is a basic component of how we can demonstrate the brain computing. The brain computing is neuron is molecular scale. People can demonstrate with a CMOS or RLM memory, resistive memory with a big scale, micro scale. But if you are scaling down to molecular scale, what will happen to? Is it still possible to molecular scale level can mimic to really electronic junction can mimic to brain computing or not? And what can be difference between the CMOS scale or molecular scale? Those are basic example that we can study the molecular junction state and understanding, and that help to other industry or itself by using itself. Those are something my philosophy.
Thank you, Takhee Lee, again for your answer and great talk.
Thank
I
you.
believe the molecular scale electronics will help us to understand the molecular system better and find some new function. Thank you, Chris. I have no more questions. Thank you.
No, thank you very much. Let's continue. Maybe now I can invite John Liu to ask questions.
Sure, definitely, Chris. Thank you so much, Professor Lee, for the great talk. So I have a question also on the molecular junction. So once the molecular junction is formed between the two metals, could you comment on potential impact of the orientation as well as the internal strain of those molecules on their electronic properties, and as a result on the electronic property of the interface? So could you comment on that?
Okay. Let's say, again, I have to use my slide. And that, to answer that, I have maybe, if I can find the backup slide, maybe I can find, like, maybe I cannot, some backup slide. Okay, I cannot find the backup slide here. Okay, here is a backup slide. The orientation, we cannot control orientation, but the molecule has automatically formed some tilting configuration or even lying down configuration with a defect. But when you fabricate molecular junction with the top, bottom, then we have an indirect method that is so-called electron molecular vibration coupling. So it's similar to electron phonon coupling. That this is a phonon coupling signal has a different peak. Okay, one is high, one is lower. That depends on whether electron passing to molecular vibration direct coupling direction. So by measuring that, so this is, for example, one is these are higher than the other component, which meaning this is rather than lighting up position, not the standing up position, not lying down position. We don't know the tilting angle. Okay, so by this indirect method, there is one way we can recognize which is the orientation. And during the measurement, molecule is not fixed. Is by temperature it can be rotated and moving around, and sometimes it can moving. That depends on the packaging of the surrounding. Actually, the polarized, they study a lot of the molecule can be bending and the switching, like bending down and in time. Okay, so but those are also possible. But if you're packing a lot, the probability of the moving, so they are polarized, they study it by depending on the packing surrounding, the probability of the molecular switching can be different. Okay, So we have to making really packing structure that to minimize these time varying properties. But molecule can in dynamic, okay? But yes, it's dynamic. But we have to make it carefully to packing and other things to minimize this dynamic problem. But what we measure, the current is kind of stable. But although there is a little bit distribution, that's due to a little bit some molecule of gold can moving around. Also, the gold is connected to the molecule and moving around on the surface. Those are dynamic property. But dynamic, how important dynamic in terms of the magnitude of current? If it's negligible, it's okay. If it's serious, there will be a problem. But so far, if you fabricate carefully that the dynamic current contribution is not severe, so I think we are okay. But that's also we have to study carefully. Okay, so then I can give you my comment answer.
I see. Yeah. So I have a second question here regarding. So probably the idea might sound crazy, but you know, for chemistry, people usually talk about activation energy of molecules. For example, the decomposition of or conversion of some say methane and things like that. But I think very few people actually pay attention to the field, which is a gradient. So I'm thinking that is it possible that we study basic chemistry process, say some sort of a capping or gas molecule or something in between a small metal gap, and then like what you mentioned, using dynamic approach to study the, you know, and use electrical characterization and nanoscale to get some hints about what's really going on when you have a field acting on those molecules. I mean, it sounds crazy probably. I don't know how to do that, but
well, I think it's in gas space or solid space, people can do that. In our solid state, it's maybe it's difficult to some sensing mechanism because we are all you know, is all blocked, isolate from environment.
I see.
But if let's say we have a matter molecule with open space, then there's a they can do something. Let's say we have a matter molecule with some ionic type, and that can penetrate with the molecule and influence the active molecule channel. They will behave as something else. That can be, you can provide some another effect. But it depends on structure. I think it's a people can really actually study that. I'm sure the people study that.
I see. Okay, thank you so much, Professor Lee. So back to you, Chris.
Okay, thank you.
Thank you very much.
Can I jump quickly onto that comment briefly?
Yeah, sure.
Yeah, so actually, June, thank you so much for your questions. And it's actually possible to pull out some chemical information from these molecular junctions. There's Chris actually pushed the boundary on this. Sorry, Chris, I'm going to toot your horn a little bit. He started talking about tilting of ferrocene in the assembly and how that tilt angle affect the behavior, because it correlates not only with the distance but also the charge ejection. He did some very beautiful work in Nature Nanotechnology, the first paper, followed by a few papers in Science and other places, and others have followed lead on that to start showing how conformation shifts and even how dipole, like two polarized molecules within two polar functional groups within the same molecule can start crosstalking if the dipole of that moiety is different. So Chris pioneered something that was very beautiful from a chemistry standpoint. And this ties back to what Professor Takhee Lee was saying, that the field of molecular electronics is not a specialist field. It's actually a collection of people. You have to bring people from physics, from chemistry, from organic synthesis to make the molecules and understand all the issues from physical chemistry. And you have to get engineers. You have to get all these people together and make them talk to each other. And so some of the things you're suggesting are actually possible. And there are people who are very, very interested in understanding those chemical processes. For example, conformational dynamics between a cyclopentane and a cyclohexane. You can actually use a you can use molecular junctions to actually reveal that information, and even how dipoles are misaligning or they're messing up as you apply the field. And I believe it's my conviction that at some point we will be able to pull out things related to energies of rotation of molecules, or even conformational dynamics in a way that we have never seen it before. So there's a lot of potential in the field. Yeah.
Yes, thanks, Martin.
Sorry, Chris. I thought I would jump there.
Oh, wonderfully said, Martin. I could not do it myself better. But yes, I think that is really now a very interesting directions this field is going to. And there is like a whole new area of nanoelectronics that is now really opening up and emerging. That is all related to emulating synaptic behavior, trying to mimic how the dynamical behavior of our brains, neuromorphic computing, and also there I think molecular junctions. Takhee Lee already mentioned it quickly. The dynamical properties of the junctions are very important to consider as well. And I think in those kind of applications you could really start to dream to exploit that to really do new forms of computation. Yes. So okay, yeah. In for the sake of time, let's move on and ask maybe Xian Wang to ask questions.
Professor Lee, very nice talk. So you mentioned Professor Macri at the end of your presentation, because I also know Professor Macri. He was a colleague of mine when he worked in Tianjin University as a joint professor.
Right, that's right.
So he actually teach several summer school lecture about bioelectronics, because our school really interested in bioelectronics. So he chose to teach bioelectronics in our school. Actually, I met him several times in campus, and we also talk about some of my research direction. So he gave me a lot of very enlightening advice about my research. I'm really thankful for his advice. I'm so sorry to hear that he passed away, because I just met him before the COVID, maybe in 2018. Last time he visited China. So I think he's a really good guy and very nice advisor, also to me as well. So regarding your presentation, I have two related questions. The first question is that because you at the very beginning of your lecture, you talk about how to improve the yield of your single molecule or monolayer devices. So the yield has improved from a few percent to 18% or even 100%. So I'm wondering that what about the repeatability of the device performance? So if all this device was fabricated in the same batch, whether their performance will be vary? And can you give me some comment about their repeatabilities?
Sure. Okay, so let me also show my slide. I think I can find. Let's say maybe I have in the backup slide. Okay, current density. So those are good. I think this is a good example. Okay, so this is also a famous issue that not only the batch to batch, from the platform technique to platform technique can be a little bit different. Let's say there's a conductive polymer high yield or graphene transfer high yield. So if you look at this, these are some are high yield platform. The yield is here is poor. This is poor because it matter. And this 90%, 50%, those are all high yield with a different graphene solution process, PDOT. Some of our other groups, I don't know what they are. Okay, so there's many ways. Okay, so here is if you look at this is some particular work, and the line this is depends on the beta value of this material choice. when you can notice that except that this color, all are quite similar of a slope. The beta value is something 0.8 to 1.2 similar, but there's a wide variation of this y this value, the J0 value. You can talk about J0 value with contact junction, which is some platform is high but poor contact, and some platform is better contact. There's some variation. So those are difference between platform to platform variation. But good news is at least we have a background is something weak contact, good contact, middle contact. But whenever you have a background, but the slope main channel effect is quite constant between among the various platforms. Okay, so within the platform, like one, this I don't know what that is, but this two is like this graphene. They also have a variation. Even one student fabricate one batch one day. I mean, imagine that today's Korea is very hot and humid. If you fabricate hot and humid, it can be terrible. Right? That's the reason why people try to fabricate in clean room with a class 100,000. Okay, so even particular day that if it's batch, but that easily recognizable. But let's say you have a one result of the one batch is totally two orders out of the high current, low current. You can look at the conventional average value. You can, if you have anything average value is outlier statistically, you can remove by scientific selection. Okay, that selection should be scientific based on scientific the basis. Okay, so usually we use the statistical basis, which is the outlier. We can when we have some 3 times sigma, some outlier, we can totally neglect that kind of categories. Then within the outlier that we have to collect or take average. That's nowadays we take average, and George Whitehead's group, they do a lot also the average statistics. We do the statistics. Now we realize the importance of statistics, which is a very important question that not only molecule, but anything nanostructure has a tiny junction area. Whenever a small 10% variation will cause a lot of variation. So they should be statistically studied. Not only one junction, how many junctions was measured? Like 10, 100, and what is the average? What is the error bar? What is the statistics? And those are really, and then if it's anything different feature is including the statistics meaning, that can be really conclusion of the science. Okay, this is something high current in considering of statistics average. And those are results. Otherwise, I already showed some example that only of the study, which is this example, only study of what is where is it? I cannot find it is right. Those are because it's not scientific statistics, not statistics. So this is why we have a different behavior. But it published at the time 2004. But at that time we didn't have any statistics. But statistics start about 2010, 9-7, and Whiteside group, our group, and another group. Now we do statistics, and we have the meaningful of all error bars. Even other even effect also should be meaningful statistics in terms of statistics, and also on-off ratio should be statistically meaningful. And I think statistics is very important.
Okay. I hope I still have some time to ask another short questions. So because you didn't go
short one, and then let's do one short one, and so that Martin also still has some time.
Okay. Okay. So my question is that since you didn't mention too much about the fabrication process of this device, I was wondering that so how to scale up the fabrication process from a single device to maybe a logic circuit, and in the future maybe to a fully integrated circuits.
Yeah. Okay. So scaling up the individual unit to many unit is one example of this, and this is scaling up of the one function, and another example of this scaling up of this wafer scale. But if you talk about integration of different function, then that's a whole new world. Okay, we are not that stage like one FET. This is FET, and how we can scale up this FET with another type of FET or CMOS FET. And we had a demonstration of the one P-type FET, N-type FET molecule, but we couldn't connect that. Okay, this depends on yield and many issues, but we are not scaled yet, but staging. But at least we have a now high yield. We can think about some integration of a different function of some logic circuit demonstration. It can be possible than before. But we can think about that, and I can think of some particular logic demonstration that we can work on that. But that's in future.
Okay, thank you.
No, thanks a lot. Okay, then I would like to give Martin the opportunity to ask a quick question.
Oh, thank you very much, Chris. Takhee Lee, as always, is always fantastic to hear a talk from you. It's always very refreshing. And thank you so much for the time you spent talking about Mark. I think Mark is an inspiration to the field and to a lot of young and upcoming scientists. And I hope that a lot of those who are in their careers and those of us in this field would embrace the spirit of going where others have not gone, like Mark did, in pursuing quantum dots and break junctions, and not giving up even when the yields were miserable. And so that spirit is something that the field needs. And thank you so much for highlighting him. He's an inspiration to a lot of us. The other thing that you brought up, and I think is characteristic of the field, is the use of statistics. And when you talk about molecular electronics, a lot of people in mathematics, do not think that this is a field they need to work on. And if you look at the way you interpret the data, the fact that we have a Gaussian distribution fit on the histogram is actually capturing the stochastic nature of the chaos in the measurement. What is your advice to those young scientists who might be interested in getting to molecular electronics? What should they be thinking about in terms of preparing themselves to really get into the weeds and push the field beyond what everybody is doing right now? What would you ask them to target based on your own experiences?
Okay. Okay. So, but I guess it cannot be limited to a molecular junction, but even the 2D material, any nano. I mean, before about 2006-07, that we didn't really know about the statistics. So there was goal to fabricate high yield first. And we even think about statistics at all. Okay, and you remember that the poor contact, good contact, and 2004 we thought that the good contact is about 1,000 times more conducting than poor contact. But by studying the statistics, it was not. It's only about 1 order magnitude difference. See? In young student, I always talk to my student also, and so if they present some result and then some ugly data, okay, and so, but even that ugly data, that you should not neglect ugly data. I mean, you have to making some histogram, heat map, and then maybe there's hidden things. It's one. I mean, it reminds me that our department professor on the space, and he gave a talk of this day of the James the space microscope, the imaging, and one image was, if you remember, the one image about like far away is like a subtle stars, but those are actually as a galaxy star. I mean, and some faculty can look at the tiny plot, and then they are studying that tiny. So there's many hidden signals in there. Even the early data, IB data. I mean, you should not give up. Like 10 data is so early. There's don't anything repeating feature at all. We have to many. Then you have to think about, is it really there's a meaningful that inside there's a search of the. Actually, I did the lab meeting yesterday, and then one first year student showed that the many early data, but summarize, plot that, and then try to find the hidden signal. Maybe there's hidden signal, so don't give up. And then do one more days, another days, another day. If it statistic is not enough, and then do more repeating, then they collect all together. And then selection should be based on scientific statistics. And then they get some good idea of the meaning. And then that we, in many papers in past my group, and actually we did the kind of process, and then try to find the meaningless hidden signal and meaningful that. And then students realize, oh, there is something there. There's something, suddenly there's memory behavior, switching behavior that's meaningful in something inside, and they should not give up and do a lot of work, and then should not give up. And there should be some hidden signal that we cannot recognize, but there is nature there is some science that this our effort and ability to try to find out, okay, from the early configuration, there is a meaningful there. There's something our job to find out, I guess. I don't know.
These are wonderful words, I think, to conclude the evening with, because I think, yeah, the importance of statistics simply cannot be overstated. Everybody can find one sampling device, but whether that is really representative and whether such a device is really going to change the world and make life better, for instance, yeah, that you can only find out by statistics, and I would say even more statistics. Well, let's conclude the evening herewith, and now my slide is going to the next one. Well, we had a wonderful evening. Takhee Lee, thank you again for giving a wonderful seminar, and I would also thank all the panel members for very stimulating discussions. Yeah, and herewith I would like to present you this very nice certificate that you delivered the talk, Takhee Lee, in volume 108. And of course, next week Friday, there will be another speaker, and that will be Peter Wang from the University of California. And he will be talking about molecular imaging and cellular reprogramming in immunoengineering. Thank you very much, and see you hopefully all next week again. Bye-bye.
Okay. Thank you. Thank you.
Great. Yeah,
Thank
great
you.
talk.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。